Hello, good afternoon. Good afternoon, everyone. Am I audible, guys? Is it visible to everyone? Hi, good afternoon, good afternoon, good afternoon. So, welcome back. Welcome back to Applications of Thermodynamics Revisions through Questions. Okay, and these are the PYQs. So, guys, today we are going to do revision where we are going to solve some of the good PYQs which have been there in the exam. And I feel there are chances that similar questions might come in the exam in this what we are going to today. What we are going to discuss today. I'm sure most of you must have already done the PYQs, but guys, this is a revision so that quickly we will solve these questions. Roughly 2 minutes or 3 minutes maximum of time we will take. सर जी लास्ट एग्जैक्ट वीक बचा है, प्लीज बता दीजिए. So, just a second, hold on a second. Okay, so बता दीजिए आपने कैसे किया था, हमको ये लास्ट वीक गाइड कीजिए. ओके, आई विल गाइड इट, डोंट वरी. So let's start the revision, guys. So in between I will keep telling what things you have to do. ठीक है, चलो. So guys, see, today we have got a full set of questions from these topics. So these are the topics which we are going to discuss today. I'm sure you know refrigeration and air conditioning, then psychometry, then internal combustion engine. We are going to discuss some theoretical cycles as well. Then we are going to discuss combustion chemistry. Finally, gas turbine, Rankine cycle, air compressors also. There has been 2-3 questions asked. There are questions asked from steam turbine, but those questions were way before, like 2014 or so. So I have not added steam turbines over here, and also this is not part of our syllabus as well. And finally, the compressible flow. So we are going to do some of the questions where I feel that these are the important questions, and they might come in the exam which we are going to see. So guys, quickly start solving the question. Okay, one by one. I am sure most of you might be knowing the answers, or you exactly know, but guys, I don't want you to just answer me what is the answer like this question. You also have to tell something related to this question which generally we don't discuss. Okay, so chalo, start one by one. I'll tell you what you have to tell me. Okay, so let's see this question. So it says, in which of the following pair of cycle both cycles have at least one isothermal process? So which are the cycles which have one at least isothermal process? Okay, quickly tell me which are the options. A, B, C, D. This is a multiple choice question. So option B, option B, option B, option B, Carnot and Stirling, they have at least one isothermal process. So diesel cycle and Otto cycle. Diesel cycle and Otto cycle. Diesel cycle has two isentropic, ठीक है, two isentropic. Then Otto cycle also have two isentropic, ठीक है, this we know. Then Otto cycle has two volume equal to constant. This has one pressure equal to constant and one volume equal to constant. So there is no isothermal process in this. So this is wrong. Okay. Carnot cycle and Stirling cycle. We know that Carnot cycle has two isothermal and two constant pressure. Okay. Pressure equal to constant. Not pressure equal to constant. PV to the power gamma. Isentropic process. So there are two isentropic, two isothermal. Whereas in Stirling cycle is two isothermal and two constant volume cycles. So volume equal to constant. We know that from Stirling we have got the Otto cycle. So actually this is the right answer. Okay. Then going to Brayton cycle and Rankine cycle. So in Brayton cycle we have two isentropic. We have isentropic 2 and pressure equal to constant 2. So these are the Brayton cycle, and same Bell-Coleman is also 2 isentropic, 2 pressure equal to constant. Rankine cycle 2 isentropic, and one is constant temperature and other is varying temperature. In fact, you can say constant pressure. Okay? So Rankine cycle, if you see, there is one isothermal process, second constant pressure process, and there are two isentropic process. ठीक है. Similarly, the last Bell-Coleman cycle, we know that this is same as your Brayton cycle but running opposite. Vapor compression refrigeration is opposite of almost the Rankine cycle, you can say. Okay, so both of these are like same to same process. So the right answer is B. Okay, chalo. Next, let's do this question. So it says refrigerant vapor enters into the compressor of a standard vapor compression cycle at minus 10 degrees centigrade, where enthalpy is 402, and leaves the compressor at 50 degrees centigrade, where enthalpy is 432. It leaves the condenser at 30 degrees centigrade with enthalpy 237. The COP of the cycle is. XC के भी questions है क्या? Yes, there are few questions which are of XC that I have added over here as well. चलो जल्दी अटेम्प्ट करो. टेल मी व्हाट इज द COP. फटाफट आंसर निकाल के दो. व्हाट इज द आंसर? अरे भाई अभी तक तो आंसर आ जाना चाहिए था. इतना टाइम थोड़ी लगता है. व्हाट इज द आंसर यू आर गेटिंग? मैं तो देख रहा था कितने लोग मेरे को कॉपी करके लिख रहे हैं और कितने लोग अपना बना रहे हैं। देखो क्या देख रखा है, एंथैल्पी H1 इज इक्वल टू 402, एंथैल्पी H2 आफ्टर द कंप्रेसर 432, enthalpy at this location it is 237, and we know that H3 is equal to H4 because in a standard vapor compression refrigeration cycle you have H3 equal to H4. So from here we can calculate work of compressor, that is 432 minus 402, that is 30 kilojoule. Then you have refrigeration effect 402 minus 237, that is 165. So COP you will get refrigeration effect divided by the work of compressor. So 165 divided by 30, that is 5.5. Okay, so COP of the cycle is 5.5. Why did we get 5.15? Those of you who have got 5.15, you have just calculated 165 divided by 32. Okay, chalo. Anyways, next, a standard vapor compression refrigeration cycle operating with a condensing temperature of 35 degrees centigrade and an evaporative temperature of minus 10 degrees centigrade develops 15 kilowatt of cooling. So refrigeration effect he has given you 15 kilowatt. Refrigeration effect is 15 kilowatt. The pH diagram shows the enthalpy at various states. Okay, so there is a pH diagram on the next page that I will show you. If the isentropic efficiency of compressor is 0.75, the magnitude of the compressor power in kilowatt is. So you have to calculate what is the magnitude of compressor power. So these are the enthalpies shown over here. It is 400 over here. This is 475. Okay, and the enthalpy over here is 250. So these are the enthalpies given. These are the enthalpies for ideal case. He has given you enthalpies as for ideal case. Okay, and he has given you compressor isentropic efficiency of compressor is 0.75. Okay, so you have to calculate. Refrigeration effect is 15 kilowatt, compressor efficiency is 0.75, and these are the values of enthalpy. So quickly calculate what will be the power of compressor. Quickly calculate. What is the actual work that you are getting? Okay, quickly calculate it. What is the power? See, what he has given you is the enthalpies at different location. So you know this is an ideal cycle. So in case of ideal cycle, if you see over here, the enthalpy of compressor while going from ideal case, it is 400 to 475. But it is given that the process is not isentropic, and he has given you isentropic efficiency. तो isentropic efficiency of compressor is defined as work theoretical divided by work actual. Okay, so if you see isentropic efficiency is 0.75. 0.75 means work theoretical. What is the theoretical work? Theoretical work is this one, 400 to 475. So 75 kilojoule per kg. So 75 divided by work actual. So what will be the work actual? So if you see, work actual would become 75 divided by 0.75, that is 100 kilojoule per kg. Okay, so this is what is the actual work that will be there. Okay, so if work actual is 100 kilojoule per kg, so if you see, the real diagram would come something like this. So it will come something like this. So this will become 500. Okay, understood? So this will become 500. So when this is 500, now he has given you the refrigeration effect. It develops 15 kilowatt of cooling. 15 kilowatt of cooling matlab refrigeration effect is 15. So refrigeration effect is 15 kilowatt. So if you see, refrigeration effect is nothing but m dot multiplied by H4. Let's say this is location 4 and this is location 1. So H1 minus H4. So H1 minus H4. So you see, when 15 is given, 15 is equal to m dot multiplied by H1 minus H4. What is H1 minus H4? It is given as 250 over here. So enthalpy at this location is 250 and 400 over here. So H1 minus H4 is 150 kilowatt, 150 kilojoule per kg. So from here you can calculate m dot. M dot will come out to be 0.1 kg per second. M dot will come out to be 0.1 kg per second. When m dot is 0.1 kg per second, now you can calculate power of compressor will be equal to m dot multiplied by work in compressor, that is 0.1 multiplied by 100, that is 10 kilowatt. Understood? Is it clear? Yes or no? Okay. So I hope everybody has understood. Okay, chalo. So let's go to the next question. So question says the relative humidity of ambient air at 300 Kelvin is 50% with a partial pressure of water vapor equal to PV. The saturation pressure of water at 300 Kelvin is P saturated. The correct relation for the air water mixture is, what is the correct relation for air water mixture? So what is the relation between P saturation and PV? Quickly. Quickly calculate. क्या आंसर आएगा? So why is it that I am getting only 3-4 answers? How about others? So we know that for relative humidity phi, we define phi equal to PV divided by PVS. Okay. We defined phi equal to PV divided by PVS. Now he has given you phi. He says phi is partial pressure, relative humidity is 50%. So 0.5 is equal to PV divided by PVS. From here, can you see PV will be equal to 0.5 PVS. Why is it that I got so many C answers? Adarsh, Ritik, Mechanical Rockstar, Somnath Gun. Is it so difficult to answer this question? Really? Is it so difficult, guys? Okay, chalo. So let's go to the next question. This is again a very good question. It says moist air is treated as an ideal gas mixture of water vapor and dry air. Molecular weight of air is 28.86 and molecular weight of water is 18. At a location, the total pressure is 100 kPa. The temperature is 30 degrees centigrade and the relative humidity is 55%. ठीक है? Given that the saturation pressure of water at 30 degrees centigrade is 4.4246 Pascal, then the mass of water vapor per kg of dry air in grams or is grams. So quickly calculate this. This is a very good question. Quickly calculate. क्वेश्चन कट रहा है. Let me check. Molecular weight is 18. Okay, I hope it is okay now. कहाँ कट रहा है यार? पूरा तो आ रहा है. चलो. $14.87. Okay. So what will be the omega? He is basically asking you omega. So now you see in omega, when we write omega is equal to 0.622 PV divided by PT minus PV. I hope everybody remembers where did this 0.622 came from. Okay, it was the molecular weight of vapors divided by molecular weight of air. It was actually molecular weight of vapors divided by molecular weight of dry air. ठीक है, multiplied by PV divided by PT minus PV. Okay, so first we have to calculate what is PV. So we know that PV and PVS is related by relative humidity. PV divided by PVS is phi, and he has given you phi is 55% and PVS is 4246. So first we can calculate PV, that is phi multiplied by PVS, that is 0.55 multiplied by 4246. So this comes out to be 2335.3 Pascal. Okay, and now you can put the other values. So omega will be equal to mv. mv is given as 18 divided by 28.84, ठीक है, multiplied by 2.335 divided by 100 minus 2.335. Okay, so this will be your answer. So 18 divided by 28.84, so 0.624 multiplied by 2.335 divided by 100 minus 2.335. So this will come out to be 14.92 grams per kg. Those of you who have written 14.87 or 14.86, 14.86 will come answer from 0.622. Guys, this is wrong, because he has already given you 18 and 28.84. Had he given not 28.84, if had he given 30, most of you would have made a mistake. If he had given something else over here, you would have made a mistake, because none of you have understood what this 0.622 is. Okay, so the right answer will be 14.92 gram. I hope everybody is getting this only. Understood? Yes? Okay, very good. So let's go to the next question. Next question says, in a mixture of dry air and water vapor at a total pressure of 750 mm of Hg, the partial pressure of water vapor is 20 mm of Hg. The humidity ratio of the air in gram of water vapor per kg of dry air is. So now he has given you something different. He has given you pressure, partial pressure of water vapor and total pressure in terms of mmHg. So quickly calculate it. What is the answer you are getting? Okay, Nemesis has got 17. 17.04. Good. Is there any scope of getting all IITs at 50 mark? Yes, you will surely get in 50 marks, you can surely get IITs. Okay. So look, what he has given you guys, he has given you that partial pressure of vapors is 20 mm of Hg. Okay. And total pressure is 750 mm of Hg. Okay. So guys, since he has given you both the units in terms of Hg, you can consider this to be a consistent pressure. Okay, both of these are consistent. Understood? So over here, now you can calculate omega will be equal to 0.622 PV divided by PT minus PV. And you can directly calculate 0.622 multiplied by 20 divided by 750 minus 20. This will come out to be 17 point. In fact, this will come out to be 0.01704. That means 17.04 gram per kg. Okay. So this is straight away. But those of you who might have tried to calculate what this pressure is, so I hope you know how to calculate mm of Hg. So mm of Hg, if you remember, pressure is written as rho gh. Okay, so pressure is written as rho into g into h. So rho is 13,600 multiplied by g is 9.81 multiplied by h is 20 mm. So 20 divided by 1000. So if you do this, you will get the PV. Okay, you will get the PV, and this PV will come out to be in Pascal, Newton per meter square. Okay. So in case he has given you, let's say he had given you 20 mm of Hg, and instead of 750, if he had given 100 kPa or 1 bar, then you can convert it into like this. Is it clear? Yes. Okay. So I hope everybody has understood. Okay. Very good. So if you have understood, now let's go to. So guys, we have finished some of the important questions on the psychometry and refrigeration and air conditioning. Now let's go to the next topic, that is internal combustion engine. So internal combustion engine, the indicated power developed by an engine with compression ratio of 8 is calculated using an air standard Otto cycle. The rate of heat addition is 10 kilowatt. So rate of heat addition is given. The ratio of specific heat at constant pressure and constant volume is 1.4. The mechanical efficiency of engine is 80%. Okay. So now the brake power output of engine in kilowatt is. So you have to calculate what is the brake power output in kilowatt. Quickly calculate it. This is a very good question which has been asked. What is the answer you are getting? Very good, very good, very good. All of you have got the answer. So, guys, what is given is it is given that the Otto cycle uses a compression ratio of 8. So, when compression ratio of 8 is given, you can calculate Otto cycle efficiency, that is 1 minus 1 over R to the power gamma minus 1. You can put this value, it will come out to be 1 minus 1 by 8 to the power 0.4. I think this will come out to be 0.56. So efficiency is given, it will come out to be 0.56. Now we know that efficiency of Otto cycle is power divided by heat supplied, rate of heat supply. So since he has given you power, he has given you rate supply. Rate supply is 10 kilowatt. So if rate of supply is 10 kilowatt, then you can calculate power is equal to 10 multiplied by 0.56, that means 5.6 kilowatt. But this power is the indicated power. Okay, this is your indicated power. Why? Because if you see the value that you get over here is the power which is developed by the cycle, and the power developed by cycle is the power available with piston. So this is the indicated power, but he has calculated, he wants to ask you what is the brake power. So we know that brake power is equal to indicated power multiplied by the mechanical efficiency, and he has given you the mechanical efficiency, so 5.6 multiplied by 0.8, so you will get 4.51 kilowatt. So almost everybody has got the right answer. So excellent, guys. Very good that you have understood the question and you solved it. Okay. So now let's go to the second question of internal combustion engine. It again says an air standard Otto cycle has thermal efficiency of 0.5. Okay. And the mean effective pressure of the cycle is 1000 kPa. This is a very good question, guys. For air assuming specific heat ratio gamma as 1.4 and specific gas constant is equal to 0.287. If the pressure and temperature at the beginning of compression stroke are 100 kPa and 300 K, then the specific net work output of the cycle is kilojoule per kg. So guys, this is an excellent question. I feel this is one of the toughest question that has been asked in applications of thermodynamics. Okay, so try to calculate. व्हाट इज द आंसर यू आर गेटिंग? T3 कैसे निकालना है? वेरी गुड, वेरी गुड, वेरी गुड। देखो बच्चों, सबसे डिफिकल्ट, इस क्वेश्चन को अप्रोच करने से पहले, आप एक वर्ड भी लिखने से पहले आपको यह सोचना चाहिए कि क्वेश्चन बनेगा कैसे। क्योंकि अगर आपने कुछ भी लिख दिया है अपने पेज पे तो दैट इज अ वेस्ट ऑफ टाइम। देखो आपसे क्या पूछ रहा है वो, आपसे पूछ रहा है व्हाट इज द स्पेसिफिक नेटवर्क आउटपुट ऑफ द साइकिल किलोजूल पर केजी में। तो आपसे पूछ रहा है डब्ल्यू, वो पूछ रहा है डब्ल्यू नेट, डब्ल्यू नेट पूछ रहा है किलोजूल पर केजी में। ठीक है, तो अगर डब्ल्यू नेट किलोजूल पर केजी में, तो डब्ल्यू नेट निकालने के अपने पास दो तरीके होते हैं। या तो एक तो होता है डब्ल्यू नेट कैन बी रिटर्न एज एफिशिएंसी मल्टीप्लाइड बाई हीट सप्लाइड, और दूसरा डब्ल्यू नेट अगर आपको याद होगा साइकिल का, तो दिस इज कैलकुलेटेड बाय पी मीन इफेक्टिव प्रेशर मल्टीप्लाइड बाय स्वेप्ट वॉल्यूम। ठीक है, बट अब ये दोनों चीज जो आती हैं, ये दोनों चीज, इट इज वेरी इंपॉर्टेंट टू अंडरस्टैंड कि दोनों में से आंसर किस में से आएगा। तो देखो उसने आपको दोनों चीज दे रखी है, उसने एफिशिएंसी दे रखी है 0.5 और मीन इफेक्टिव प्रेशर दे रखा है 1000। तो अब यूज किसको करेंगे? तो यूज करने के लिए देखो, क्या हमें उसने ये दे रखा है, ये दे रखा है, तो क्या उसने स्वेप्ट वॉल्यूम दिया है क्या? पता नहीं। क्या उसने हीट सप्लाई दिया क्या? पता नहीं। तो सबसे पहले हमें पता करना पड़ेगा व्हाट इज द हीट सप्लाइड। तो हीट सप्लाई कैलकुलेट करने के लिए हमें पता है हीट सप्लाई इज CV इंटू T3 माइनस T2। T2 तो चलो मैं कैलकुलेट कर लूंगा, बट क्या T3 आएगा? T2 कैसे कैलकुलेट करते हैं? T2 कैलकुलेट करते हैं T2 इज इक्वल टू T1 R की पावर गामा माइनस 1। ठीक है, तो ये तो आपका आ जाएगा। ठीक है, बट क्या यहां से T3 आएगा? नहीं। तो सो गाइस दिस you cannot calculate. So now we are left only with one option, that is W net is equal to P mean effective pressure multiplied by Vs. Okay. So now how do we calculate this Vs? So guys, to calculate this Vs, what he has given you is, he has asked you W net per kg. That means kilojoule per kg when he is asking. That means you have 1 kg mass flow rate of the air, mass flow rate of air is 1 kg. So if this is 1 kg, so what you can do is you can take your cylinder, okay, and he has given you that at the starting of the piston, at the starting where the compression stroke is starting, he says the pressure is 100 kPa, temperature is 300 Kelvin. So now what you assume is you take 1 kg of air over here. So when you take 1 kg of air over here, can you calculate what is the volume V1? Yes or no? Yes, we can calculate volume. We know that P1 V1 is equal to MRT1. So V1 can be calculated as M is 1 multiplied by R is 287 multiplied by 300 divided by 100 kPa, that is 100 multiplied by 1000. So over here you will get 0.86 meter cube. So you have got V1. Okay, now from this V1, can you calculate Vs? Yes, we can calculate Vs. How? So for calculating Vs, you know that if, let's say, this is the clearance volume, this is Vc and this is Vs. So we know that Vs plus Vc is 0.86. Okay, Vs plus Vc is 0.86. Now he has given you efficiency is equal to 0.5. Do we know that 1 minus 1 over R की power gamma minus 1 is equal to 0.5? This is the ratio. This is the relation for calculating efficiency. So from here you see you can calculate R. R will come out to be 5.65. So when you have understood R, now you can calculate what is Vs and Vc. ठीक है? So when R is 5.65, you know that R is nothing but Vs plus Vc divided by Vc. Okay, this is 5.65. Okay, so this can be written as Vs by Vc plus 1 is equal to 5.65. From here you can calculate Vs by Vc is equal to 5.65, and you also have Vs plus Vc as Vs plus Vc is equal to 0.86. So from here you can calculate Vs. How much will you get Vs? It will be 4.65 multiplied by 0.86 divided by 5.65. So it will be 0.86 multiplied by 4.65 divided by 5.65. Understood? I hope this is what you will get. So Vs you will get from here, and now when you multiply this Vs with your P mean effective pressure, so W you will get, that is 1000 multiplied by 0.86 multiplied by 4.65 divided by 5.65. What is the answer you are getting? I hope this will be 708, what everybody has been getting. Something like that. Yes? Okay. Has everybody got that only? 1000 multiplied by 0.86 multiplied by 4.65 divided by 5.65. So 708. Okay. So 708 kilojoule per kg. Okay. Understood? This is one of the best question that I have seen in some of the years in internal combustion engine. One of the best questions. Is there anybody who has got a problem, who has not understood how we have calculated this? I hope everybody has understood. If all of you have understood, show me a thumbs up. Show me a thumbs up, sir. We have understood everything. Is it clear to everybody? Yes, clear? Okay, very good. If it is clear, so then guys, let's go to the next question. Okay, chalo. So next question says a vehicle powered by spark ignition engine follows air standard Otto cycle. Gamma is given as 1.4. The engine then generates 70 kilowatt while consuming 10.3 kg per hour of fuel. The calorific value of fuel is 44,000 kilojoule per kg. The compression ratio is. Calculate what is the compression ratio. Easy peasy. Very good. Okay. So what we have to calculate is, so you see, he has given you the power developed. Power is equal to 70 kilowatt. Okay. And when he has given you what is the fuel flow rate and the calorific value of fuel, what he is actually giving you, he is giving you what is the heat that is supplied. So let's say if I want to calculate what is the heat supplied per hour. So heat supplied per hour will be 10.3 multiplied by 44,000. So 10.3 kg multiplied by 44,000. This is the heat supplied per hour. But you have to calculate per second. So if we divide it by 3600, then this becomes per second. So you see the answer would come out to be 125.88 kilojoule or kilowatt. You will see. Okay? So this is the heat supplied. 125.88 kilowatt is the heat supplied, and you have 70 kilowatt as the power developed. So can we calculate what is the efficiency of cycle from here? So you will see that the efficiency will be 70 divided by 125.88. This will come out to be 0.55. Okay, that is what you will get it. So once you have got the efficiency, now you can use the formula 1 minus 1 over r ki power gamma minus 1 to calculate r. So r will come out to be 5 point, how much you are getting? Sorry, 7.61. I hope very easy question. Everybody must have got it. Yes? Okay. Understood? Chalo. So if you have understood, then let's go to the next question. Question on diesel engine. A diesel engine has a compression ratio of 17 and cutoff takes place at 10% of the stroke. Assuming ratio of specific heat as 1.4, the air standard efficiency. Calculate what is the air standard efficiency. So compression ratio 17 and cutoff takes place at 10% of the stroke. Efficiency 0.59. Prabhat Kumar has written 82.73. What is the cutoff ratio you are getting alpha? What is the cutoff ratio you are getting? Very good, excellent. So guys, we know that for calculating efficiency in diesel engine, you need to calculate alpha. And it is given that the cutoff takes place at 10% of the stroke. So we know that alpha minus 1 is equal to length of the stroke, that is 0.1 multiplied by r minus 1. ओके, सो दिस इज सर बार बार ऐड आ रहे हैं, क्या करूं? प्रीमियम सब्सक्रिप्शन आता है इसका एक, वो ले लो। ओके, तो अल्फा माइनस वन इज इक्वल टू लेंथ ऑफ द स्ट्रोक, जहां पे कट ऑफ where the cutoff is taking place multiplied by r minus 1. So you see this is 0.1 multiplied by 17 minus 1 is 16. So 16 multiplied by 0.1 is 1.6. ठीक है? And then alpha minus 1, from here you will get alpha equal to 2.6. Now once you have got the alpha, now you can calculate efficiency of diesel, that is 1 minus 1 over r to the power gamma minus 1. Diesel efficiency we know, how do we write? So alpha minus 1 we write like this, and to the power gamma, and in the bottom gamma like this. So once you put the values, that is 1 minus 1 over 17 to the power 0.4 multiplied by 2.6 to the power 1.4 minus 1 divided by 2.6, 1.4 multiplied by 2.6 minus 1, you will get the efficiency to be 0.596. Okay, understood? Okay, so I hope everybody has got the same answer, so apart from one, so that's very good. So now let's do one more question on the basis of the combustion chemistry. It says air contains 79% nitrogen and 25% oxygen on a molar basis. Methane is burned with 50% excess air. Assuming complete combustion, the percentage of nitrogen in products is. This is very good question, excellent question. Calculate the value. What is the answer? 55.63. Okay. So how do we solve this? So we know that it is methane. So when methane has to burn in presence of oxygen and nitrogen, that is air. So first we will calculate what is the stoichiometric air fuel ratio that you will have. So we know that for every mole of oxygen we have 79 by 21 moles of nitrogen, because it is given over here 79 nitrogen and 21 oxygen. Understood? So now we will calculate what are the combustion products. So CO2 plus H2O plus nitrogen. Okay. So since it is CH4, so you have 4 hydrogen atoms are there. So you will have 2 moles of H2O. Then you have 1 carbon. So you will have 1 mole of CO2. Now remaining oxygen. So 2 oxygen over here and 2 oxygen over here. Total 4 atoms of oxygen. So you will have 2 O2. But now he says this is the stoichiometric. But he says not only stoichiometric, the methane is burned with 50% excess air. So when 50% excess air is there, you will have 3 moles of oxygen plus 79 by 21 nitrogen. Okay, and when there are 3 moles of oxygen and 79 by 21 nitrogen, you see that now in the combustion products you will have CO2, 1 mole of CO2 and 2 moles of H2O. This will be there. But apart from that, remaining, so apart from carbon and hydrogen you see over here, now there will be an excess molecule of oxygen. So you will have 1 O2, and then remaining you have 3 multiplied by 79 by 21 nitrogen. So 3 multiplied by 79 by 21 moles of nitrogen. So you see how many moles will be there over here. So 1 plus 2, 3, 3 plus 1, 4, 4 plus 3 into 79 by 21. So total number of moles will be equal to total moles 4 plus 3 into 79 by 21, and percentage of nitrogen will be equal to 3 into 79 by 21. This is the nitrogen which is available, divided by 4 plus 3 into 79 by 21. So this is what will be your value. How much is the value you are getting? How much is the value you are getting? So 3 into 79 by 21 is 11.28. So 11.28 divided by 4 plus, that is 15.28. Okay. So the answer will be 73%. Why everybody got 55%, 59%? Because you guys have forgotten this 3. Huh? Why 79 by 21? Why you were not able to get the right answer? Tell me. I hope everybody has understood. Okay. So if you have understood, then guys, let's over here we have finished the IC engine. So now let's go to the next topic, that is Brayton cycle. So the compressor of a Brayton turbine plant operating on an ideal intercooled Brayton cycle. So ideal intercooled Brayton cycle accomplishes an overall compression ratio of 6 in 2-stage compression process. Intercooling is used to cool the air coming out from the first stage to the inlet temperature of the first stage before its entry to the second stage. Air enters the compressor at 300 Kelvin and 100 kPa. If the properties of gas are constant, then the intercooling pressure for minimum compressor work is. What will be the intercooling pressure for minimum compressor work? Quickly calculate it. What is the answer you are getting? What is the answer? Guys, this is very easy question. It should have taken hardly 30 seconds. Very good, Somnath. So guys, it is given that, see, all this tigadam jigadam, ठीक है? This he has given just to confuse most of you. So guys, what he has given is, he says that there is an intercooled cycle, and in the intercooled cycle there is perfect intercooling. So this is the location 1. ठीक है? This is location 2, this is location 3, this is location 4, and your cycle is moving like this. This is your P low and this is your P high. So he says P low is 1 kPa, 100 kPa. ठीक है? And overall pressure ratio, that is P high divided by P low, is 6. So that means what is P high? So P high will be equal to 600 kPa. So now what he is asking is, what will be the minimum pressure? What will be the pressure Pi for minimum work? So we know that Pi is equal to, Pi for minimum work is square root of P high multiplied by P low. Understood? So this is square root of 600 multiplied by 100, and you know this will come out to be 244 kPa. So intermediate pressure is 244 kPa. Very good, Somnath, Khushbu, Prabhat. How about rest of the people? Why didn't you get the answer? Okay, chalo. So let's go to the next question. It says the pressure ratio across a gas turbine with constant specific heat Cp 1040 and ratio of specific heat gamma 1.4 is 10. So the pressure ratio is 10. If the inlet temperature to turbine is 1200 Kelvin and the isentropic efficiency is 0.9, the gas temperature at the turbine exit is. This is a very good question. So solve this very easy question, hardly take 30 seconds. What is the answer? What is the answer you are getting? Very good, Somnath. Khushbu is getting 561. How come you are getting 561? So Khushbu used the formula that is there in isentropic efficiency of compressor. किसने किसने आइसेंट्रोपिक एफिशिएंसी ऑफ कंप्रेसर का फॉर्मूला यूज किया है? तो व्हाट ही सेज इज एक टरबाइन है जिसके अक्रॉस कंप्रेशर रेशियो 10 है, यहां पे 1200 केल्विन टेम्परेचर है, and if the isentropic efficiency is 0.9, so find the exit temperature, that is T4. So how do we calculate this T4? To calculate the T4 you have to calculate T3 by T4s, that is equal to P3 by P4s की पावर गामा माइनस 1 और गामा. Okay, and this will be 10 की पावर 0.4 divided by 1.4, that is 1.93. So T3 by T4s will be 1.93. So from here you can calculate T4s. I think that should come out to be 621. T4s will come out to be 621 Kelvin. So once you have calculated 621 Kelvin, now you can go for isentropic efficiency of turbine. So isentropic efficiency of turbine. In case of turbine, the work lower is the actual work, and this is your theoretical work. So you have W actual divided by W theoretical. So this will be your Cp T3 minus T4 divided by Cp T3 minus T4s. So you see Cp will cancel. T3 is already given 1200. So 1200 minus T4 divided by 1200 minus 621. So from here you can calculate T4. T4 should come out to be 679. T4 can never be less than T4s. T4 can never be less than 621. So those of you who have got 560 or so, that is because you have made this opposite. Okay. So that is the efficiency of compressor. Efficiency of compressor is isentropic efficiency, isentropic work of compressor divided by actual work. Sir, T4s and T2s में कंफ्यूजन है, कोई ट्रिक बता दीजिए कि ना भूलें. T2s, what do you mean by T2s? What is this sign? What do you mean by this? What is this? Or somebody tell me, you must have seen in the thermodynamics, what is this V divided or V under script T? See, these are temperature while keeping pressure constant. This is what is the meaning. When somebody writes in the here something like this, that means it is at constant pressure. So similarly, when you write Ts, that means temperature at constant entropy. When you write T2s, that means T2 with constant entropy. Understood? Yes. So this is constant entropy. That means isentropic temperature. I hope everybody understood. Okay. Very good. Chalo. So let's do another question. Isentropic turbine or refrigeration problem होता है. Where do you get the problem? Isentropic, there is nothing in the refrigeration where you have non-isentropic process. So a gas turbine with air as the working fluid has an isentropic efficiency of 0.70 when operating at a pressure ratio of 3. So there is a turbine which has isentropic efficiency 0.70 when the pressure ratio is 3. Now the pressure ratio of the turbine is increased to 5. So now the pressure ratio has been increased while maintaining the same inlet condition. Inlet conditions are same. Assume air as the perfect gas with the specific heat gamma 1.4. If the specific work output remains the same for both the cases, that means work output of the turbine remains the same. If work output remains the same, then what is the isentropic efficiency of the turbine in second case? This is an excellent question. Quickly calculate. What is the answer you are getting? See, what he is saying is, let's say there are two cycles. He has done modification in one of the cycle. So he says in first cycle the pressure ratio is 3. Okay, so you are coming from, let's say, location, this is your location 3 and this is 4s1, and from here you are coming to location 4-1. Okay, so this is what is the first case, and he says isentropic efficiency of turbine isentropic efficiency of turbine 1 is 0.7 in the first case. So 0.7 is T3 minus T41 divided by T3 minus T4S1. So this is what is 0.71. Now in the second case, he says that the pressure ratio is increased, okay, and pressure ratio is increased to 5. So let's say this inlet condition is same. This is 4S2 and this is your 4.2. Now he says work input remains same, work output of the turbine remains same. If the work output of turbine remains same, that means this T3 minus T4, T42. Okay, so isentropic efficiency of turbine 2, that will be equal to T3 minus T42 divided by T3 minus T4S2. So you see, these are the two efficiencies. Now he says work remains constant. If the specific work of this and specific work of this case, both the case remain same. That means what is the specific work per kg of the airflow? So if T3 minus T42 and T3 minus T41 is same. So he says T3 minus T41 is equal to T3 minus T42. Okay. So if this is the case, then you see over here T3 minus T41. Okay. This can be written as T3 minus T42. So both these are same. So from here can you calculate? It is T3 minus T42 will be efficiency of turbine 2 multiplied by T3 minus T4S2. So this will become T3 minus T42. So you can replace this over here. T3 minus T42, whatever the value you are getting, and T2, this value you can put over here. So you see, you will get efficiency in the first case is 0.7 is equal to 0.7 is equal to T3 minus T41 will be equal to NT2 into T3 minus T4S2. Okay. So efficiency of turbine 2 multiplied by T3 minus T4S2 divided by T3 minus T4S1. Okay. So now how do we calculate this NT2? So to calculate NT2, what we will do is we will divide the top and bottom by T3. So when we divide right hand side by T3 in numerator and denominator. ठीक है. So when you divide them by numerator in numerator and denominator by T3, this will become 0.7 is equal to efficiency turbine 2. Efficiency turbine 2, and this will become 1 minus T4S2 divided by T3. ठीक है. And you will have over here 1 minus T4S1 divided by T3. Now what is T4S2 by T3 and T4S1 by T3? So you see, in the second case he has given the pressure ratio is 5. Okay. So T3 by T4S2, that is equal to P3 by P4S2 इसकी power gamma minus 1 over gamma, and you know this ratio is 5. So T3 divided by T4S2 will be equal to 5 to the power gamma minus 1 over gamma. Okay. So it will be 5 to the power gamma minus 1 over gamma. What is 5 to the power gamma minus 1 over gamma? 5 to the power 0.4 divided by 1.4. That is 1.58. ठीक है. Similarly, for the bottom case, you can calculate T3 by T4S1 is equal to P3 by P4S1 to the power gamma minus 1 over gamma, and here the pressure ratio is given as 3. Okay. So 3 to the power 0.4 divided by 1.4. So 1.36. So it will come out to be 1.36. Okay. So once you have calculated both these two values, now you can put the values over here. So you will get efficiency, that is 0.7 is equal to efficiency turbine 2, 1 minus 1 divided by 1.56, and in the denominator you will have 1 minus 1 divided by 1.36. Okay. So this is 1.58. Okay. So you can do it like this. So now you can calculate NT2. So this NT2 will become 0.7 multiplied by 1.36 minus 1, 0.36 divided by 1.36, and this will be 0.58 divided by 1.58. Okay, so you can calculate this and you see it will come out to be 0.7 multiplied by 0.3, 0.31 multiplied by 1.58 divided by 0.58 and divided by 1.36. So 0.43. This will be the right answer. I hope everybody has understood it. Is it clear? Is it correct? I hope everybody has understood. Yes, this was a very good question. Okay. So now let's go to one more question. It says, now this question is on steam power plant. It says, in a steam power plant based on Rankine cycle, steam is initially expanded. Steam is initially expanded in a high pressure turbine. The steam is then reheated in a reheater and finally expanded in a low pressure turbine. The expansion work in the high pressure turbine is 400 kilojoule and in the low pressure turbine is 850 kilojoule, whereas the pump work is 15 kilojoule. If the efficiency of cycle is 32%, then the heat rejected in the condenser is. This is a very good question. This is a very good question. Fatafat calculate it. Okay, so quickly calculate it. Two 624. Very good. Very good. So you see what is the W net? If you see over here, the work of turbine 1 is 400, work of turbine 2 is 850. So work of turbine W net will be equal to work of turbine 1 plus work of turbine 2 minus work of pump. Okay. So what is W net? W net will be equal to 400 plus 850 minus 15. that is 1235 kilojoule per kg, and it is given as the efficiency is equal to 0.32. Okay, so if efficiency is 0.32, you can calculate what is the heat supplied. So heat supplied will be equal to 1235 divided by 0.32. How much it will be? So heat supplied will be 1235 divided by 0.32, that is 3859. ठीक है, 0.3 kilojoule per kg. And once you have calculated heat supplied, now you can calculate heat rejected. So heat rejected will be minus 1235. So 2624.375 kilojoule per kg. I hope everybody has got the same answer. Yes, everybody has got the same answer. So excellent, guys. Very good. Okay, let's do one question on the regeneration. So it says consider the open feed water heater shown in the figure. Specific enthalpy of steam at location 2 is 2624. Oh, we got the same answer in the last. Okay, so enthalpy at location 2. I hope it is visible to everyone. This is your location 2. This is your location 5. This is your location 6. Specific enthalpy of water at location 5 is 226.7 and specific enthalpy of saturated water at location 6 is 708. If the mass flow rate of water entering the open feed water heater at location 5 is 100 kg per second, then the mass flow rate of steam at location 2 will be. So what will be the mass flow at location 2? $25.16, $25.16, what is the answer you are getting? Quickly. Okay, so how do we solve this question? So guys, you see, you have to balance on the open feed water heater. So it is location 2, this is location 5 and this is location 6. Okay, so you see that mass flow rate at location 5 multiplied by enthalpy at location 5 plus mass flow rate at location 2 plus enthalpy at location 2 will be equal to mass flow rate of 5 plus mass flow rate at location 2. ठीक है, multiplied by enthalpy at location 6. Okay, so this is what you will get the equation. So M5 into H5 plus M2 into H2 will be equal to M6 into H6. So now you see, you can write this. You can write this equation: M5 H5 plus M2 H2 is equal to M5 H6 plus M2 H6. Okay. So now you can club this 5 and 2. So you can write M5 or M5 you can take onto that side. So M5 into H6 minus H5 will be equal to M2 into H2 minus H6. Okay. This H6 you will bring onto this side. So M2 H2 minus H6, and this M5 you will take onto that side. So now you can solve this equation. M5 is 100, 708.6 minus what is 226.7 will be equal to M2 into 2624 minus 708.6. So from here you will get M2, that is 25.16 kg per second. Okay, so this is a very easy question on the feed water heater. Okay, I hope everybody has understood this. Okay, next. So this is again a very easy question based on the Rankine cycle. So which of the following modification of the simple ideal Rankine cycle increases the thermal efficiency and reduces the moisture content of the steam at the turbine outlet? So quickly, what will be the answer? So which of the following increases efficiency? So in the basic Rankine cycle, I hope everybody remembers what is the basic Rankine cycle. Basic Rankine cycle is this. So which of the modification leads to higher efficiency and reduced moisture content? Decreasing the boiler pressure, increasing the boiler pressure, increasing the turbine inlet temperature, decreasing the condenser pressure. So if you see decreasing the condenser pressure, that means your cycle would be moving like this. And if your cycle is moving like this, decreasing the condenser pressure would increase the efficiency, but it will reduce the moisture content. It will increase the moisture content. So dryness fraction will reduce. So this is wrong. Efficiency will go up, but X will drop. But what he is asking is efficiency should also decrease, and moisture content should also decrease. Increasing the boiler pressure. Increasing the boiler pressure increases the efficiency. It increases the efficiency. Efficiency again increases, but dryness fraction reduces. So this is also wrong. Decreasing the boiler pressure. Decreasing the boiler pressure is the opposite of this. So efficiency reduce, dryness fraction increases. So this is also wrong. Increasing the turbine inlet temperature. So when you increase the turbine inlet temperature, that means you are making the cycle to go in the superheated region. So when you are putting it into superheated region, at that time your efficiency increases because of this higher temperature, and your dryness fraction also increases. So this was very easy question, guys. Okay, I hope nobody should have any doubt regarding that. Okay, next, it says steam enters a well insulated turbine and expand isentropically throughout. At the intermediate pressure, 20% of the mass is extracted for a process heating, and the remaining steam expands isentropically to 9 kilopascal. Okay, so what happens is there is a turbine. I hope there is no diagram. So there is a turbine over here, and you see the process happens like this. Okay, so the process is like this. So the main pressure is 14 megapascal, and at 20% at an intermediate pressure, your 20%, that means if this is 1, then 0.2 kg is extracted out for process heating. Okay, and finally it expands to 9 kPa. So over here it is 9 kPa. So he says if the inlet condition pressure is this, temperature is 560, H is 3486. So over here H is 3486 and entropy is 6.6. So if these are the two conditions, okay, then at intermediate stage enthalpy is 2776. Exit of the turbine at 9 kPa, your enthalpy HF, HG, SF, SG. If the flow rate of steam entering the turbine is 100 kg per second, then the work output, you have to calculate what is the work output. This is an excellent question. ठीक है. I hope everybody has written the previous data. So you can write the previous data, that is at this location H3 is 3486, H3 and H4 3486 and 6.6, 3486 and 6.6. फटाफट calculate what is the power output developed by the turbine. What is the answer? Okay. See. So how do we solve this question? So guys, if you see over here, let's say this is location your 3. Okay. So let's say this is location 3. This is location 4 and this is location 5. So first we need to calculate what is enthalpy at location 5. So to calculate enthalpy at location 5, you know that we know that S5 equal to S3, that is 6.6. So first we need to calculate what is the dryness fraction. So S5 will be equal to 6.6 and S5 can also be written as SF plus X time Sg minus SF. So SF is given as 0.6 plus X time 8.1 minus 0.6 and this is given as 6.6. So you see from here you can calculate X dryness fraction will come out to be 0.8 and once dryness fraction is 0.8 you can calculate H5 is equal to HF plus X times Hg minus HF. So HF is 174 plus 0.8 times 2574 minus 174. Okay, so from here you will get the answer to be 2094. 2094 kilojoule per kg is the enthalpy H5. And once you have calculated H5, now you can calculate work of turbine. So work of turbine will be equal to H3 minus H4 is the complete expansion, plus remaining expansion is 80%. So 0.8 times H4 minus H5. Okay. So you see work of turbine will be equal to H3 minus H4. What is H3? H3 is given as 3486. So 3486 minus intermediate 2776. So it is 2776 plus 0.8 times 2776 minus 2094. So this is the work that you will get per kg of the steam flow. Okay. So H3 minus H4 is 3486 minus 2776 plus 0.8 times 2776 minus 2094. So 1255. So you are getting 1255.7 kilojoule per kg. But he has given you the mass flow rate of the steam at entry is 100 kg per second. So if mass flow rate is given as 100 kg per second, then you can multiply this 1255 with 100. So power of the turbine will be equal to m dot s multiplied by work of turbine, that is 100 multiplied by 1255.6. Okay, so you will get 125.56 megawatt. Power of the turbine is 125.56. I hope everybody has understood. Yes. Yes, is it clear? Okay, very good. So now let's go to the next question. My goodness. Okay, so again, I think while the background is actually dark gray or dark maroon, you can say. So the values were in black. I think these are not visible. Okay, so you can consider this to be numerical answer type question. So it says a steam, the value of enthalpy of steam at the inlet and outlet of a steam turbine are 2800 and 1800 kilojoule per kg. And neglecting the pump work. So you have to neglect the pump work. He is asking what is the specific steam consumption. So quickly calculate what is the specific steam consumption. So what is specific steam consumption? specific steam consumption is 3600 divided by W net, and this will be in kilowatt. Okay, so 3600 divided by W net is work of turbine minus work of pump. So work of pump is neglected. So work of turbine. So turbine inlet enthalpy is 2800 and exit is 1800. So work is 1000. Okay, so 3.6 kg per kilowatt hour. Okay, so everybody has given me the correct answer. So Mechanical Rockstar and Somnath, you should have checked your answer beforehand. So no issues. Okay, so now we have finished the steam turbine. Now let's go to the questions of this is a question of compressible flow. Okay, so we have now few questions of compressible flow. So quickly calculate. Consider adiabatic flow of air through a duct. At a given point in the duct, velocity of air is 300 meter per second, temperature is 330 Kelvin, and the pressure is 180 kPa. Assume that the air behaves as a perfect gas with a constant Cp. The stagnation temperature at this point is. Quickly calculate. Quickly calculate. $373. Very good. Very good. So how do we calculate? Stagnation temperature T naught is equal to T 1 plus V square divided by, or what you can write is if you want to if you don't want to get confused, let's say if you remember the formula, then you can directly write Cpt naught. This is the total enthalpy, that will be enthalpy plus V square divided by 2. Okay, most of the student get confused over here, what will come, gamma or gamma minus 1. So what you can write is H plus V square divided by 2. So H you can write Cpt plus V square divided by 2. You can write it like this, Cpt naught. Okay, so from here you can write T naught is equal to T plus V square divided by 2 Cp. ठीक है, so T naught is 330 plus 300 square divided by 2 into 1005. This is what is given, no? 300 meter per second, temperature is 330 K, and the pressure is, consider adiabatic flow. Okay. So what will be the answer? 330 plus 300 multiplied by 300 divided by 2 divided by 1005. So 374.77. 374.77. ठीक है. Many of the student would also like to attempt this in a different way. ठीक है. So lot of you student, those who remember the formula of T, okay, you can calculate this as 2 plus gamma minus 1 by 2. M square also you can calculate, and M can be written as M square is equal to V square divided by C square, and C square you know that it is written as gamma R T. Okay, so you can solve it like this as well, V square divided by 2 gamma R T. ठीक है? Understood? Okay, very good. Let's go to, I think this is the second last or last question. Okay, this is the third last question of the day. Okay, so in a 3-stage air compressor, the inlet pressure is P1, discharge pressure is P4, and the intermediate pressure are P2 and P3. The total pressure ratio of compressor is 10, and the pressure ratio of the stages are equal. If P1 is equal to 100 kPa, then the value of pressure P3 is. So this is a question, very easy question of multi-stage air compressors. So what he is asking is, if the pressure ratio is same, then what will be pressure P3? So P1, P2, P3, P4 are there. Okay. So you have to calculate what is ratio P3. What is pressure P3? So this is a very easy question. What is the answer? Very good. 464.15. Very good. So we know that the pressure ratio is same. That means P2 by P1 is equal to P3 by P2 equal to P4 by P3. That is constant K. So from this relation we can calculate P4 by P1 is equal to K की power 3. Okay. So we can calculate P4 by P1. So you can write P2 is equal to P1K. Then you can put P1K over here. P3 will become P1K square. P4 will become P1 K cube. So P4 by P1 is equal to K cube, and it is given as 10. So from here you can calculate the value of K. Value of K will be equal to 10 to the power 1 by 3. So once you have calculated K equal to 10 to the power 1 by 3, this will come out to be 2.27. Okay, so this will come out to be 2.27. So guys, now he is not asking you P2. So P2 will be equal to P1 multiplied by K. That is 227 kPa. Instead, he is asking you P3. So P3 is equal to P2 multiplied by K. So that is 2.27 multiplied by 227. So this will be 464 kPa. Okay, so this you have to understand, or this you have to see very clearly what he is asking. So he is asking what is the ratio P3, what is the value of P3. So P3 will be equal to 464.16. Okay, chalo. So now let's go to the last question, second last question of the day. Okay, so this is a question on convergent divergent nozzle. It says consider a steady flow through a horizontal divergent channel as shown in the figure with supersonic flow at the inlet. So the flow is supersonic over here. Okay, and while going from location A to B, the direction of the flow is from left to right. So while going from location A to B, pressure at location B is observed to be higher than that at upstream location A. So he is saying pressure at B is higher than pressure at A. Okay, generally in a divergent section, okay, when you see when the supersonic flow is there, divergent section will behave as a divergent nozzle. But you see, he says the pressure over here is more than the pressure at location A. Then which among the following options can be the region? So what is the region for this? Guys, this is an excellent question. So it says since volume flow rate is constant, velocity at B is lower than velocity at location A. So he is asking what is the region of higher pressure. So he is saying velocity at location B is higher than, B is lower than the velocity at location A. Normal shock, viscous effect, and boundary layer separation. Okay, this is a multiple choice question. So guys, you have to tell me what is the answer for this. What is the answer? Velocity at location B is lower than velocity at location A. So you see the statement, first statement is correct. If you see first statement is correct, this is a correct statement, but this is not the reason for correct. This is a correct statement. Volume flow rate is constant. In fact, sorry, this is again not constant. So volume flow rate is not constant. Volume flow rate is changing. It is increasing. Okay. Velocity at B is lower than velocity at A. This is correct. Okay. But why velocity at B is lower than velocity at location A? Because you see, when the pressure is higher, increase in pressure is caused due to reduction in velocity. So you see, increase in pressure is caused due to reduction in velocity, and that reduction in velocity has actually come because of presence of a normal shock wave over here. So if the pressure is increasing in a divergent section, that means there is a normal shock present over here. Okay, it was supposed to have a supersonic flow, and it was supposed to have a low pressure downstream. But suddenly there is an obstacle present, and because of that obstacle, let's say if you have a supersonic flow, when you have a supersonic flow, suddenly when there is a object present, what happens? Suddenly, let's say you have an object present, what happens? You see that there will be a shock present. Understand? And because of that shock, the velocity reduces. Understand? So the same thing happens in a nozzle as well. If there is an obstacle, if somehow the high pressure is created, then that pressure created would lead to a normal shock over here. Okay, so this was an excellent question which was asked in 2022 exam. Okay, and the main reason for that is the presence of a normal shock at the downstream. Is it clear? Very good. So now guys, let's go to the last question. This is the last question of this PYQ session. So it says an object is moving with a Mach number of 0.6 in an ideal gas environment which is at temperature of 350 Kelvin. The gas constant is 320 joule per kg Kelvin and ratio of specific heat is 1.3. The speed of the object is, he is saying what is the speed of the object? It is moving at Mach number 0.6, gas constant is 320 and specific heat is 1.3. So this is very easy question. सर 23 चॉइस का PYQ नहीं लाए थे? अरे 23 चॉइस के क्वेश्चन तुमने ऑलरेडी किए हुए हैं तो क्या जरूरत है लाने की? PYQs तो आप लोगों ने एकदम घोट के पिए हुए होंगे, मुझे ऐसा लगता है. जो PYQ का सेशन है दैट इज नॉट इवन वर्थ इट. So what is the answer you are getting? 228.94. Prabhat, that is the correct answer. So you see, if Mach number is given and he is asking velocity, so you know that Mach number is equal to velocity divided by the speed of sound. So from here you can calculate velocity is equal to Mach number multiplied by speed of sound, and speed of sound is under root gamma RT. Okay, so he has given you all the three values. So velocity will be equal to 0.6 multiplied by under root gamma, that is 1.3, multiplied by 320 and multiplied by 350. So from here you will get answer to be 228.9 meter per second. This is very easy question. Okay, understood? Very good. So if you have understood, then guys, we have come to end of today's lecture. I hope you must have got some idea, okay, what type of question we are expecting. Okay, though you must have done all the PYQs, you have the book, you have the video solution, so everything is available there. But this revision we had brought so that you can at the last moment we can have some revision. Okay, so I hope you guys have had a good experience. Okay, so best of luck guys. I suggest that you attempt the paper and try to get maximum marks. Okay guys, remember that if you are able to score 50 marks, then probably you will get a good IIT. Okay, so top IITs you can get, so try to get at least these marks. Don't go for 90 marks if you are not very confident. Don't go for 80 marks. If you are able to comfortably score 65, 67, 68, 69, that is a much better score. Okay, okay, I don't say that you should not aim for 100. You should aim for 100, but in the search for 100 you should not fall into a situation where you are not getting only 40. Okay, so try to get whatever you can get. Okay, but at least get 50. Okay, so chalo, sir, that's all. Thank you so much. Okay, see you after the exam. Best of luck. ठीक है, thank you.